All right, let's do more physics. Cannons go boom. They're exciting. So let's do some exciting stuff with projectiles. So earlier we learned about horizontal launches, which were boring. These are going to be angled launches, which are exciting. So we've got a guy who's going to fire out a cannon. He's firing it at a 35-degree angle. So I'll draw that in right here. So we got a 35-degree angle from here to here. And its initial velocity of 100 meters per second. So this thing is just flying off at 100 meters per second. Okay, we want to figure out three things. 1, max height. 2, max distance, aka the range. And 3, the time of the flight. Now these can be solved in pretty much any order you want. But to get a better picture, let's draw what the entire flight path will look like, because sometimes you need to know what the entire thing looks like to figure out where to start. So if we fire this off, it's going to have a parabola. And we know that our initial launch right here is 100 meters per second at an angle of 35 degrees. And we want to know max height, max distance, and time of flight. So there's actually several ways of answering all these questions. So it's really up to you about what information you want to gather. For fun, I'm going to treat each one as if it's totally unique, totally independent, and then as we go on, I'll talk about how some are actually related. So let's just do them in order for fun. So we'll go max height. So that means I'm going to go from this location here to this location here. So I have to ask myself, what do I know? And since projectile, we want to keep the x-plane and the y-plane totally separate. So x-plane separate from y-plane. Now, first thing we want to know is usually what's the velocity in the x-plane? Well, if I look at this is at an angle, so I'm going to have to break that up to its components. So to break it up into its components, in the x-plane I'm going to use cosine, because this really is a triangle that looks like this. So this is my x, this is my y, and that's my v. And so this is my angle of 35 degrees in this case. And so if I want to figure out the x piece, it is adjacent to my angle, so I'm going to be using cosine. So what I really have is cosine of 35 degrees equals Vx over V. So if I want to solve this universally, the x component is equal to V cosine of whatever angle I'm looking at. So over here where it says Vx, I'll give myself a little more space. So I've got Vx equals 100 cosine of 35. Still didn't give myself enough space. Oh well, c'est la vie. Actually, I'm going to just do this. Oh look, it disappeared. Let's make it reappear. Ooh, magic tricks. All right, now, in the x-plane, I don't know anything else. That's all I'm given. But in the y-plane, I can find the initial velocity the exact same way, except here we're going to look at the y piece, and the y piece is opposite the angle. So this is going to be using sine. So sine of the angle is equal to the y component divided by the hypotenuse. So multiply both sides by v, I really get the universal of vy equals v sine of theta. All right, so this is going to help me solve pretty much, or I should say break up any angled launches into their x and y components, because we can only live in the x world or the y world. We cannot live in both. So this right here is then going to be 100 sine of 35. What else do we know about the y-plane? Well, it's in free fall, because if we draw a force diagram, the only force acting on it is gravity. So we know it's in free fall, so we know the acceleration is negative 9.8. because it's accelerating down. We are then going to say, is there anything else we know? Well, we're looking for that max height. So it's delta y. That's what we're looking for. So we need another piece of information. Well, at our max height, something interesting happens. Your velocity in the y-plane becomes 0, because this is where you turn around. All right? So our velocity equals 0. And if you don't believe me, just draw a velocity time graph in the y-plane. We start off going in the positive direction, and over time the object had a negative acceleration, And at some point here, we get a velocity equal to 0, which is our peak. Oh, look, it's like everything we've learned so far, force diagrams, graphs, trig, it's all coming together. All right, great unit. So now I have enough information to solve for this max height. So I'm going to do that. So to find the max height, I have to use all this information. And the equation that's going to get me there is going to be v squared equals my initial velocity squared plus 2 times my acceleration times my displacement. So now I just substitute in what I know and solve for that displacement. So I know my final velocity is going to be 0. So I got 0 equals 100 times sine of 35 squared plus 2 times negative 9.8 times my vertical displacement, and so I can solve. And my vertical displacement is, drumroll please, dun dun dun, 167.85 meters. So that is our max height. All right, so that's the first one. Now, the second thing we were asked to do was find the maximum distance, also known as the range. So I'm going to still use this. I'm going to pick a different color to work in. I don't know why. Let's go red. Red. All right, so now we're looking for max range. So now we're trying to figure out what is this. So that's delta x is our unknown. And so now, some things are going to change in here. So 1, we're now looking for this. And 2, our final velocity is no longer 0. So this is no longer a truth for us. What is a truth are actually 2 options. The first one is just by looking at this, we start on the ground, we end on the ground. So instead of our displacement being unknown, we now know our displacement is 0. And so now we can try and solve for our unknown. And the link between the y and the x, you guessed it, time. So if I can find time here, I can use it over here. This is one way to solve the problem. A second way to solve the problem is to understand that if you land at the exact same height that you're launched from, you'll have the exact same velocity just in the opposite direction. So we could have also said that our final velocity is negative 100 sine of 35. Now granted, that only works, again, I'm stressing this, that only works if you have this perfect parabola where you end at the exact same height you were launched at. If you don't land at the exact same height, this is not a true statement. Okay? I mean, neither is this, but this might be a number. This is based purely on this situation. So I'm not going to use that to solve this. I'm going to use this guy right here. So if we want to find the range, now we're definitely have to do a 2-step problem, because we're going to have to solve for time in the y and then use that in the x. So to solve for time in the y, it looks like the equation we're going to have to be using is delta y equals v sub naught delta t plus 1/2 a delta t squared. I'm sure you've memorized all these equations by now. And we know our displacement is 0. Initial is 100 sine 35. I'll just put some delta t plus 1/2 negative 9.8 delta t squared. Now, you could punch this in your calculator if you need the quadratic. You can solve it that way. So again, if this is not 0, you're going to have to do that. Use the quadratic equation. But since it is 0, we can do a little bit of a trick here. So I'm going to show you the trick for when it's 0. So we got 0 equals, and then we can actually factor out a delta t. And so then that's going to be 100 parentheses, sine of 35, because we factored out the t, so that's gone, plus 1/2 times 9.8 delta t. So now either this equals 0 right here, or this equals 0. Well, this first time equaling 0 makes perfect sense because that's when it was kicked. So if we solve for when this is equal to 0, we can figure out when it hits the ground. So that's what we're going to do. So really we're going to use the equation 0 equals 100 sine 35 plus 1/2 times 9.8 delta t. Solve for time, and we get 11.7 seconds. All right, so that's not the end of our problem, but that's our time. So now that we have time, we can then put that into our x here, because we now know that the time is 11.7 seconds. So now we can say, well, I can solve for the x-plane because it's constant velocity. The only equation that we're going to use is the equation for constant velocity, which is this guy. And we know that the x velocity was, go back to short one, 100 cosine 35. So 100 cosine 35 equals our displacement, which we do not know, times the time, which we now have, and we can now solve for how far this thing goes. And we get 958.4 meters. So that is how far it's actually going to go. And you'll notice that by doing this, I actually solved for the flight time as well. So I did actually solve for that along the way to getting its max range. Now, there's some other ways you could have done this. Okay, it is possible, and these are often because it is a perfect parabola. You could have looked at it and said, well, you know, if I want to break this down, I could say, well, if I look at my parabola, so I'll draw a new one here. Some things that we know about parabolas is that if it's a perfect parabola, that is not a perfect parabola. When it gets here, the time it takes to go halfway is exactly equal to the time it takes to go the other half. So if you wanted to, we could have used the information and said, hey, I'm going to figure out how much time it takes to reach its peak, and then double it to figure out the overall time. That's another option. Like I said, we could also say that we know that the velocity here is the exact same, be it opposite of the velocity here. Of course, in the x-plane, it's just constant the entire way, never changes. And here at the peak, the velocity in the x-plane is constant, but the velocity in the y-plane is 0. So those are a few things you can use if it is a perfect parabola. If it's not a perfect parabola, then you're definitely going to be using that quadratic equation to solve things like we did over here for time. And that's okay. You've got that under your belt. You know, worst is you find it on the internet or something like that. But that is how you solve for angled launch problems. First things first, do your trig, break it up. And then it's just like our horizontal launches, the math's a little uglier. All right, hope that was helpful. See you on the flip side.